A strength of covalent bonds. Basically, a strength of a covalent bond determines the stability of a molecule, and stability of molecule is related to chemical reactivity. So indirectly I can say a strength of a covalent bond is related to reactivity of a molecule. First it is related to stability, and then it is related to chemical reactivity. So a strength is related to molecular stability, and stability is related to chemical reactivity. So what I want to say, let us discuss more. A strength of a covalent bond is related to a stability of molecule. If I have higher strength, bond, then molecule is more stable. So I will have more stable molecule. Now molecule is more stable, this means molecule does not want to convert into atom. So I can say molecule is less reactive, so chemically less reactive. Now other way around, we can say if molecule has lower strength, if molecule is low strength bond, it is less a stable molecule. This means molecule can be easily converted into atom. So it can easily convert it into atom, it can react very easily, so I can say chemically more reactive. For example, let us say if I say chlorine and iodine. Chlorine has more a strong bond, iodine has weak bond. So I have chlorine chlorine and I have iodine iodine. This bond is a strong bond and this bond is a weak bond. So I can say chlorine is more stable, less reactive. Iodine is less stable, more reactive. So iodine is more reactive and it is less stable. And this is in the comparison with chlorine. Now let us discuss bond enthalpy. Let us say I have a diatomic molecule. I have chlorine molecule. Chlorine has two atoms. It can be shown something like this. And this bond, chlorine-chlorine bond, so I can idealize this bond by a spring. So this bond is equivalent to a spring. Now let us say what happens if I give some energy to this chlorine molecule. Initially it is vibrating with this much amount of amplitude, that is this much amount of distance. If I give energy, it will still vibrate, but now it will vibrate with slightly longer amplitude. So amplitude becomes longer. If I give some more energy, a time can come when these two atoms can basically fly apart, and the corresponding energy is related to bond energy. So this energy required to make atom free, we are calling this as a bond energy. So what is happening here? If I give energy to chlorine molecule, it can be converted into chlorine atom, and the corresponding energy, that is the energy I have to give, is related to bond energy. Now what is bond enthalpy? This is again related to bond energy. So let us say I have chlorine gaseous molecule, and let us say if I take 1 mole of chlorine gaseous molecule and if I give energy, then it can be converted into chlorine atom, and this is of course gaseous. So in this case the amount of energy required is called bond enthalpy. So we have definition for bond enthalpy. So it can be said energy required to convert 1 mole of gaseous molecule into gaseous atom. When we say enthalpy, enthalpy term is related to basically 1 mole of substance, and if I simply say bond energy, so this is related to 1 bond. So if I say bond energy, this is related to 1 bond, and if I say bond enthalpy, this is related to 1 mole of bond. So this point is important. For example, if I have chlorine gaseous atom molecule, it can be converted into chlorine atom. This is gaseous and this is also gaseous. And if I take 1 mole of chlorine, corresponding energy required is 242 kilojoule per mole. So bond enthalpy for chlorine is 242 kilojoule per mole. So I can say bond enthalpy for Cl2, and this is equals to 242 kilojoule per mole. So bond enthalpy will have a unit of kilojoule per mole, or it can also be written in terms of kilocalorie per mole. So unit for bond enthalpy, and bond enthalpy or bond energy is sometimes written as Be. This is kilojoule per mole, or it can be kilocalorie per mole. And if bond enthalpy is not so strong, then in that case we can say joule per mole, or it can be calorie per mole. Some important point, we said for diatomic molecule, let us say chlorine molecule is a diatomic molecule. We have chlorine, chlorine, only single bond we have. In these cases, defining bond enthalpy is very easy. So it is relatively simple to define bond enthalpy of diatomic molecule because it has only bond. There are molecules that has more than one bond. In those cases, defining bond enthalpy is slightly difficult. In that cases, so in case of complex molecule that has more than one bond, we define average bond enthalpy. Let us say, for example, we have a CH4 molecule, and if I write Lewis dot structure for CH4, we have this molecule is CH4. Now we have 4 CH bond, so there are 4 CH bond. I am interested in what is the bond energy of CH bonds or bond enthalpy. So we are interested in bond enthalpy for CH bond. So how we can do? Let us remove CH bond one by one, or let us atomize CH4. So we have CH4 here, and if I remove this one hydrogen carbon hydrogen bond, so I will have CH3. So basically we are removing this bond, so I have CH3 plus hydrogen. In this case, let us say we require x kilojoule per mole energy. Now if I remove next CH bond, if I remove this CH bond next, I will have CH2 plus hydrogen. But now in this case, we will not require x kilojoule per mole energy, because you see, environment of this carbon hydrogen bond is different than environment of this carbon hydrogen bond. This carbon hydrogen bond has a different environment because at this point of time carbon is connected by 4 hydrogen, and at this point of time carbon is connected by only 3 hydrogen. So these two species will have different environment, and that's why in this case energy required to remove this carbon hydrogen bond is different. Let us call this as a by kilojoule per mole. Similarly, we can remove one more hydrogen from this molecule, so I have CH2 molecule, and if I remove, I will have CH plus one more hydrogen. In this case again energy will be different. Let us call this a by kilojoule per mole. And if I have this molecule now, if I remove one more hydrogen, I will have carbon atom and hydrogen atom, and in this case let us say we have Z kilojoule per mole energy. If I see, we can write a overall reaction. What is happening overall? This cancels, this cancels, this cancels, so we will have CH4, and this gives you carbon plus 4 hydrogen, and bond enthalpy will be X plus by plus Z plus W kilojoule per mole. If you see what we have done, we have broken 4 carbon hydrogen bond. Now we can define average carbon hydrogen bond energy. That is this divided by 4, because we have removed 4 carbon hydrogen bond. So we can define average bond enthalpy in this case, and this is sum of the bond enthalpy divided by number of bonds. In this case we have number of bonds is 4, so X plus by plus Z plus W divided by 4. So we can define average CH bond energy X plus by plus Z plus W, this divided by 4, and the value of X plus by plus Z plus W from experiment, it is found that this comes out to be 1660 kilojoule. So now we can calculate average CH bond energy. This is 1660 divided by 4, so this is 415 kilojoule per mole. But now you see, in defining bond average bond energy of CH bond, we have taken only one compound, that is methane. And that is not true. There are many compounds that contains carbon hydrogen bond. We have CH4, we have C2H10, we have C2H4, we have C2H2. There are large number of compounds that contains carbon hydrogen bond. So if I want to more accurate value of carbon hydrogen bond, we have to take average for a large number of molecules. So if we consider many other compounds containing carbon hydrogen bond, average bond energy comes out to be 413 kilojoule per mole. So if I consider only methane, average bond energy is 415, but if I consider a large number of molecule, this value is 413 kilojoule per mole. So now I can say average bond energy of CH bond is 413 kilojoule per mole. Similarly, we can define or we can calculate bond energy of different bond, CH bond, CC bond, CN bond. So these all are single bond. So these can be calculated from experiment. Similarly, we can calculate bond energy for single, double and triple bond. So this is single bonds and this one is double and triple bond. So in double and triple bond cases also we can calculate bond energy. So you see CC double bond energy has a 614 kilojoule per mole and single bond energy has a 348. So general double bond will have more energy than single bond and triple bond is even more stronger than the single bond. And these things we will derive in the next slides. So let us say one example. How can you use the enthalpy of atomization of hydrocarbon ethane, that is C2H6, along with the bond energy of CH. So CH bond energy is given, to estimate the value for carbon-carbon bond energy. So what is the thing that is given? So we have been given average bond energy for carbon hydrogen bond, and let us say this is x kilojoule per mole, and this value is given. This is 413 kilojoule per mole, and we have to calculate bond energy for carbon-carbon bond. So we have to calculate this value. Let us call this value is y kilojoule per mole. And we have been also given enthalpy of atomization of ethene. So we have been given enthalpy of atomization ethane, and this is equals to, let us say, z kilojoule per mole. So this value is also given. So we have to calculate bond energy of carbon-carbon bond. So you see we have C2H6. If I atomize this molecule, we will have 2 carbon plus we will have 6 hydrogen. So energy of enthalpy of atomization for this reaction, that is given z kilojoule per mole. Now if I want to atomize this molecule, we have to break 6 carbon hydrogen bond. So we have to break 6 carbon hydrogen bond, and we have to also break 1 carbon-carbon bond. So these are the bond that has to be broken. This means I have to give energy to break 6 carbon hydrogen bond, and the bond energy for carbon hydrogen bond is x. So we have to give 6x energy, and we have to give carbon-carbon bond energy, that is by kilojoule. So we have to give 6x plus by kilojoule per mole energy. And now this energy that is given, that is heat of enthalpy of atomization, that is Z kilojoule. So this is Z kilojoule per mole. So from here we can calculate by is nothing but Z minus 6x. So if I know Z and if I know X, we can calculate by, that is bond energy for carbon-carbon bond. Some important point about the bond enthalpy. Bond enthalpy is always positive quantity. That is, we have to break the bond. So if I have a molecule AB, I have to break the bond. That means I have to give energy. So delta H for this reaction is always positive. So we have to give energy to break the bond. So that's why, since there is a breaking of bond, it has to be positive. The reverse is negative. That is, formation of bond will release energy. So if breaking of bonds requires energy, formation of bond will release energy. So I can say formation of bond, the reverse, will release energy. Now next important point we have, greater the bond enthalpy, stronger is the bond. This we have seen from the last. You see CC bond you can have CC double bond, you can have CC triple bond. In this case, bond enthalpy for carbon-carbon bond, you see the chart, we have the table. So the previous slide, carbon-carbon bond is 348 and carbon-carbon double bond is 614 and carbon-carbon triple bond, that is 839 kilojoule per mole. So these are the energy. So I can say carbon-carbon single bond has energy of 348 kilojoule per mole and carbon-carbon double bond has 614 kilojoule per mole, and this has 839 kilojoule per mole. So now I can say carbon-carbon bond is a less stronger than carbon-carbon double bond and carbon-carbon triple bond is most stronger. So I can say carbon-carbon triple bond has highest energy, and then it is carbon-carbon double bond, then we have carbon-carbon single bond. So this is a strongest bond, and this one we have, this is a weakest bond. So idea is clear. If you have bond energy is higher, bond is stronger. Now another important point, molecule with higher bond enthalpy is chemically less reactive. This is obvious. If I have A to B, AB molecule, if I give energy to convert into A plus B, and the energy required, that is higher, so delta H is a high value. This means this has less tendency to convert it into atom. So correspondingly I can say this is chemically less reactive. Let us say an example. If I have nitrogen molecule, this is my nitrogen molecule and this molecule is N2H4. Now in this case, this bond is basically a strong bond, carbon-carbon triple bond. Triple bond is always stronger than nitrogen-nitrogen single bond. So this bond is basically single bond and it is a weak bond, so it can easily break. So I can say hydrazine, that is N2H4, can easily break, but this nitrogen, this bond is a stronger bond, it cannot easily break. So now I can say N2H4 is more reactive. So chemically this is more reactive. Let us do one exercise. Based on bond enthalpies, which do you expect to more reactive, oxygen or hydrogen peroxide? So we have O2, this molecule is O2, and this molecule is hydrogen peroxide H2O2. Now our task is to decide which molecule is more reactive, and this is easy. And this can be done on the basis of bond enthalpy. Here we have double bond and here we have oxygen-oxygen single bond. So this bond is a weak bond. Single bond is always weaker than double bond. So this bond is weak bond, so it can easily break. Oxygen-oxygen single bond. So now I can say H2O2 is more reactive than O2. So if you see, in this lecture we have discussed the concept of bond strength, and we discussed in terms of covalent bond, and we said a bond is stronger, it is less reactive. And then we said how to calculate average bond enthalpies. So we said we have to basically atomize the molecule and sum all these enthalpies and then divide by number of bonds. Then further we said single bond is less stable than double bond, and correspondingly with the triple bond, that is triple bond will have highest bond enthalpy than single bond or double bond. And finally we said bond enthalpy can be used to decide whether molecule is less reactive or more reactive.